Okay, hopefully you've constructed the graphs. And I'll also say right here at the beginning, there is one significant difference between the graph you get here and the graph you get here. And I wonder if you can tell me what that big difference is in the shape of the graph. You should think about that before you view further. I'm going to stop a couple of times here and tell you to do that. Okay, see if you get it right. Okay, first, let's graph the, let's construct the graph for the f of x function. Now, x goes up to 6, so I'll put 6 here for the x scale, and then we can divide that into 2 equal parts, hopefully equal. And we can put 1, 2 here, 4, 5 here. And the slopes go from 0.1 to 2.2. So let's just put 2 right here, leaving us a little bit of room above. And we'll divide this. We'll have 1 here. We'll have 0.5 here. 1.5 here. And that should give us enough numbers to at least get an approximate position for each of these points. So x is 0.8 when the slope is 0.1. So 0.8 is here just a little bit back from 1, and 0.1 is 1/5 of the distance from here to 0.5. So that's going to give us a point, I think, right about here. Okay, then when x is 3, the slope is 0.75. Now 0.75 is going to be halfway between 0.5 and 1. So 3 and halfway between 0.5 and 1 gives us a point. I don't have a real good angle with the board here, so don't hold me responsible for getting these points located with any precision. Okay, anyhow, we get this. And then when x equals 6, the slope is 2.2. So 2.2 is going to be up here quite a bit further. And let's see if I can locate that point. Okay, so there are 3 points on this graph. Also, we know that the graph is flat at the beginning, or at least we can conjecture that, and we can confirm that if we need to. So I can actually have a 4th point on this graph. And these 4 points are going to connect with a smooth curve. Okay, well, I can do the same thing over here. Now, if you haven't already done it, look at what I did, stop the video, and by doggone, do it. Okay, maybe you can do it in your head. Maybe you can visualize accurately what it's going to look like. One way or another, you're responsible for doing it, otherwise you're going to have less understanding. You know, it doesn't take long to do it. Okay, so same thing over here. Here's 6, 3, 1, 2, 3, 4, 5. So 1, 3, 6. And now the slopes go up to 1.3. So I'll put, I'm going to say 1. Didn't leave myself a lot of room here. Okay, that's 1.5. And then I'll divide that into equal parts. So I've got 1 and I've got 0.5. Hopefully you can read that. That point is not separated very well from the 5, but I think you know what we mean. Okay, so at 0.6, which occurs a little more than halfway between 0, at x equals 1.2, which occurs between 1 and 2, somewhat closer to 1, we get a slope of 0.6, which would be about here. So we have a slope of 0.6 at 1.2. We've also got, again, a slope of 0 when x equals 0. We haven't proven that, but it's so, and you might think of how it would be proved. Okay, anyhow, then we get up to x equals 3, the slope goes up to 1.15, and that's going to be maybe about, actually a little higher than that, about here and here, so we got a point here. And then at x equals 6, we got a slope of 1.3. So we come all the way out here, and we've got this point. Okay, now, what's the difference between the shape of this graph and the shape of this graph? Okay, well, hopefully you see it. If you don't, we can always connect the points with a smooth curve. On each graph. Now, what's the difference between the shape of this graph and the shape of this graph? Well, I will say that, now this is the graph for f of x. The factor is 0.8. 0.8, I don't know where I got 0.8. It's 2.5. There's a 0.8 laying around here somewhere and kind of, my eye must have caught it. Okay, but the y factor here is 2.5, and the graph is increasing faster and faster. Okay, it's increasing at an increasing rate. And we can also express that as saying the graph is concave up. Concave up. If you're in the cave looking out, out is up. Okay, here, this is the y factor. What? Y factor is 6. And the graph is increasing at a decreasing rate. Okay, so and it's concave down. Now, you should actually do this to convince yourself of it. Y factor 2.5 and something is okay, I've got something labeled backwards here, and I've had it all along. The f of x function had the y factor of 6. The g of x function had the y factor of 2.5. And that might have been somewhat confusing. I'll try to annotate the videos in such a way as to warn you about that. Clearly, the y factor here is greater than the y factor here. I simply wrote these down carelessly, and I haven't really used those factors since I constructed the graphs. Okay, so the y factor here is I'm going to write it down wrong again. Y factor is 6. And the y factor here is 2.5. So let's get the 6's replaced. And 2.5 here. .5 here. Okay. Okay, I apologize for any confusion. But now let me say what I started to say. Okay. It might make sense if you think about it that a bigger y factor causes the graph of the slope, causes the slopes to increase more and more quickly. Okay, so that gives us then a concave up graph when we graph the slope versus the position, slope of a tangent line versus the position. Okay, a smaller y factor means that the slopes are not going to increase as fast. As a matter of fact, the slopes increase at a decreasing rate when the y factor is only 2.5. That shouldn't be too surprising, again, if we think about why that is. Now, whether you really understand flight comes out that way or not, you should get the idea that the bigger the y-factor, the faster the slope increases. Okay, bigger y-factor increases slope more quickly. Okay? Excuse me. And from this we can raise the question of whether there's actually a slope excuse me, that increases at a constant rate. If we're increasing at a decreasing rate for a certain smaller y-factor, and then at an increasing rate for a certain bigger y-factor, well, as we keep making the y-factor bigger and bigger, the concavity should decrease, and at some point we'll go from concave down to concave up at some value of the y-factor. We'll go from concave down to concave up. And that factor in that graph give us sort of a cusp in the behavior of these functions, and it's actually the number, the y-factor, that gives you the straight line, the slopes versus point of tangency lying along a straight line linear graph through the origin. That's really a very important function, one of the really important functions for application to the real world. So that's kind of a big deal. Okay, well, we'll talk more about that in a minute.